Hello again. This video we're going to do chapter 9, and it's on assessing studies based on multiple regression. Mostly it's about things that can go wrong and mess up either your estimators of the betas or the estimators of the standard errors, which then messes up the test statistics. So it's basically, how can we tell if an estimated model is reliable? What are some of the problems you should look for? And we're going to do this through a framework where we have something called internal. So it's going to be assessing internal and external. External is what that word's supposed to be, validity. And I'll explain what these mean in a second here. So that's sort of the framework we're going to use. And to evaluate internal and external validity, we need to talk about some concepts here. First of all is the population studied, and that's just the population of entities, people, firms, the population, just using the book's definition here of entities, people, firms, school districts, to use one of our example, and so on, whatever the population we're studying is, from which the sample is drawn. And we'll see how this relates in a few moments to, particularly to external validity. And so one thing that this will depend upon is the population studied. And the other thing is the setting where the study was conducted. So the institutional, legal, social, and economic environment. So you may do a study on tomato yields in the lab. So that's the setting. And then the question is going to be, will it apply to the field as well? Can we take the results from one setting and apply them to another? And that'll be part of external validity. Or suppose we do this class size study for California, as they've done. Can we apply those results to Massachusetts or Tennessee or some other state? To what extent are the populations and the settings identical enough to allow you to do that? So let's be a little more specific about this internal and external validity. What exactly we're talking about. So threats to internal validity. This is within the sample. Internal means sort of within the sample, the population, the sample from the population within the particular setting. So within this setting and for the given population, to what extent are your estimates good? So internal validity has two components. Has two components. One, the estimator of the causal effect that we're interested in should be unbiased and consistent. So these are the betas. That's the estimate of the causal effect. Otherwise, you're going to get invalid answers. Let me switch pins here. I think I have a darker one. And so we're trying to learn about the truth. What's the true value of the MPC? What's the true relationship between investment and the interest rate? So if the coefficient's biased or inconsistent, it's not going to tell us the right answers. And that would also mess up test statistics. And so that would be that sort of. Otherwise, you get invalid answers. Secondly, the hypothesis test should have the desired significance levels. So basically what we're saying here is, this is the beta hats. This is mainly the sigma squareds. So we want the standard errors unbiased, say correct, for example. See, if you're doing like a t-test, t is beta hat minus the hypothesized beta. Beta, say h, hypothesized, this is actual, over sigma of beta hat, standard error of beta hat. This test could go wrong if the betas are misestimated. If they're biased, you'll get a biased test statistic, and that'll mess up your significance levels. You won't get the true significance levels. And if you have the sigmas here are biased for some reason, that's also going to bias your test statistics and give you the wrong answers. So you need to have a procedure that gives you both the correct betas and the correct sigmas, and you need to assume the right distribution for your test statistics. You don't want to assume an F when it's something else, or assume it's assume the wrong distributions. And so for OLS, under our assumptions, you do have unbiased and consistent estimators, beta hats, and you do have sigma hats are calculated in a way that gives a correct significance levels. That's why we use the heteroscedastic robust standard errors, because if we have heteroscedasticity and we don't use that estimator, we're going to get a bad estimate of the sigma hats. The heteroscedastic robust estimator works even for the homoscedastic case. So it's not inconsistent in that particular case. And it also works for the case where you have heteroscedasticity, obviously, because that's what it's designed for. The regular sigma hats, the ones that don't allow for heteroscedasticity, those can get you into trouble if you actually have it. So again, we're looking at internal validity right now. That's how well we estimate the actual sample. So we have this data that comes from some population. It's done within some setting. It's done in the lab, or maybe it's historical data. Maybe we design an experiment. However, whatever the setting is, given that setting, given that population, internal validity is we've got the correct beta hats, we've got the correct inference from beta hats, the correct causal inference, and we've got correct test statistics. And the correct test statistics is, for the most part, that you have the right estimator of the standard errors. Okay, threats to external validity. And here what we're talking about is just what we were saying before. You might have a certain population in a certain setting that you estimate in. So we do a school study for California. To what extent can we take those results then and apply them to some other state like Massachusetts? The tomato plants in the lab, will that transfer to the real world? If we're doing experiments on mice, will those work for people? Those sorts of questions. So to what extent are our answers valid external to the population, the setting we actually studied? So there's two sources, and they're just exactly what we just said, two sources of threats. I'll come back to internal validity in a little bit and talk about all the threats. Mostly I just wanted to define these things. We didn't quite, in section 9.2 we'll come back to internal validity. Sorry, I didn't write down all the ways in which we can have internal validity go wrong. I'm going to come back to that. So how can external validity go wrong? Two ways: differences in populations. Maybe income levels are different, or the demographics are different, or that aren't accounted for in the X's. And so if the populations are very different, it may be that your results won't hold, because that population, the California results have a whole lot of immigrants in there that are making a difference. Maybe in a state with no immigrants, you're going to get a different sort of result. Maybe there's other differences in the populations as well. And so if there's big differences in the two populations, then the results just might not be applicable. Secondly is differences in setting. Suppose we're studying how the number of police patrolling the street affects speeding. Well, it may be that the fines are different in the two states. It may be that the geography is different. A lot of uphill and downhill might make a difference. When people get on the downhill, they might speed more. You might have small town versus large town differences, things like that. There could be legal differences in terms of the fines. I think I already said that, or the way the courts handle these things, whether you lose your license or not, all sorts of things. And so if you don't control for all those different things, then a study done for this city may not apply to this other city because their settings are so different. How would you assess external validity? Well, one thing you could do, say you had the school study, you could collect some data for Massachusetts and just do a quick sort of pilot study, a little small thing, and see if the results look consistent. Those sorts of things. You can think about potential differences that might cause things to go up, that might cause there to be differences in the two things, that might cause the results not to apply externally. And what you can, the best thing you can probably do is think about it beforehand. So I'm going to estimate it for California, but I want to apply it to Massachusetts. So what are the differences between those two states I would need to control for? And as long as we put the controls into the model, as long as we design the model correctly, so we're controlling for all the things that are different, then we're going to be much more likely to have the results be externally valid. So you'd want to include, if there's differences in immigration, an immigration variable, so you can control for that. And other sorts of things. And so you want to include a variable for income to control for that if there's some difference in income. Maybe the school years are different lengths, or maybe there's other differences. As long as you control for those in your study, you're much more likely to get results that are externally valid. You could also do it for California. Take a sample of a few other states, Texas, Massachusetts, maybe one or two more. Do the same study in these states, and if it looks like the results apply in these very different sort of, we think maybe Texas and Massachusetts are very different in terms of in a lot of ways, but yet the results hold, then you might be much more confident that you can apply it to all the states, to Colorado or Washington or Idaho, Nevada, whatever, and so. You might be much more willing, having done a few checks on the external validity by doing independent studies in these other states, to say, okay, it probably applies generally to all 50 states. But again, you'd want to think hard in each case if there was any difference between the states that you haven't really accounted for in your model. Some states might have very unique things that matter. So you need to think. Okay, threats to internal validity of multiple regression analysis. This is section 9.2. And I've got a little slope to my writing. Not the first time that's happened, is it? external validity is largely a matter of experimental design, again, including the right controls, making sure that your results are going to hold for the other populations and so on, and other settings. So you're controlling for all those differences across states. And so if you design your experiment well, you're probably going to have a better chance at external validity. Internal validity relies upon again, we've said this already, unbiased and consistent estimators. And secondly, correct standard errors for tests. And I would say that, and also you assume the correct distributionals, made the correct distributional assumptions. So we're going to start off with the first one. We're going to look at 5 different ways this could go wrong. Then we'll look at the ways this could go wrong. There's 2 main ones here where you can get messed up: heteroscedasticity and serial correlation. And there's a bunch of ways that you can get unbiased coefficients, all of which involve. So let's look at that first one first. There's 5 ways that we'll talk about internal validity might not hold. And they all, the problem in every case is that the correlation of x and the error term does not equal 0. Remember, we've said that when you have this problem, you automatically get bias and inconsistency whenever your x's and your u's are correlated. And so there's lots of different ways in which that correlation can happen. One we've already looked at, and that's omitted variable bias. And so we don't have to spend much time on this other than to just put it on our list. Remember here, if it's correlated with the x's and causes y, then you'll get bias and inconsistency. The solutions to omitted variable bias, how to solve: add the variable if you have it. That's the best solution. Oh, I've left out income. Let me collect some data on income and put it in my model. There's something called instrumental variable regression that can solve this. You'll do that in 421. Basically, you find a variable that's correlated with x but uncorrelated with the error term. And that can be hard, but if you can find such a thing, and often you can sort of use that instrumental variable in place of the x, because it's correlated with x but uncorrelated with the error. And there's a fancy estimator that uses both x and the other variable to come up with an unbiased, consistent estimator. And so IV estimation is a good way. IV sort of can generally overcome this correlation problem. So you find another variable z that's correlated with x but uncorrelated with the error term. And then you use the IV estimator that you'll learn in 421. Basically the sum of the x. Before it was the sum of the xi minus x bar to y minus y bar over the sum of the xi minus x bar squared. It becomes the sum of the, if z is a variable, zi minus z bar times y minus y bar over the sum of the xi minus x bar times the sum of the zi minus z bar. And so that particular estimator is unbiased, and you can show that fairly easily, but I'll let the people in 421 do that. Randomized controlled experiments are a way to avoid this problem, because when you randomize, you break the correlation. Say there's an omitted variable z in your error term. Well, if you do your experiment right, all of your right-hand side variables are independent. You've designed it in a way that the x is going to be uncorrelated with all the stuff in the error. And there's techniques to do this. I said, when I was an undergraduate, I took a class called experimental design, and we learned how to orthogonalize our treatments. And so in your experiment, you made sure that your x's were absolutely uncorrelated, so you can choose the x's in a particular way, because you're choosing the treatments and observing the outcome of the y's. So you just choose your treatments when you design your experiment to avoid any possible omitted variable bias, because you break this correlation with the x's. And so randomized controlled experiments are another way to get around this problem. I'm not going to be able to explain this, but in the very first lecture, we talked about panel data. That's a cross-section that we follow through time. In panel data, there's a way to do this. You basically, you add, they're like dummy variables. You can control in panels as long as the effect is constant over time. Don't worry about that too much at this point, because we haven't really talked about panel data at all in this class. And that's not something you do a lot of in 421, but you do a little bit. But most of this stuff, adding a variable then is the best solution. And this is saying randomized controlled experiments, if you can do it, but we have historical data, so often we can't. These other ones are telling you that there are ways to solve it. You'll learn them in later classes in 421. Right now, we're telling you what to look out for. And what you look out for the most part, is omitted variable bias. And so to the extent that you can, you want to include all the variables that seem important in the model. And that's the best way to overcome the omitted variable bias. This was basically, the next one is basically what Chapter 8 was all about. Misspecification of the functional form can lead to bias. So suppose the relationship between y and x is nonlinear, but we estimate with a linear model. That can cause bias and inconsistency. You're not going to get the right parameters. You haven't modeled the data very well. For instance, suppose you need a quadratic term and you've left it out. Then you're going to get a bias, because if the true model is yi is beta 0 plus beta 1x plus beta 2x squared I plus ui, and you leave that in the error term because you've left it out of your model, well, those two are correlated. X and x squared are going to be correlated. And so you've got something in your error term that belongs in the model that's correlated. So that's going to cause beta 1 to be biased. And so misspecification of the functional form. This is like an omitted variable bias, but maybe I need a log model. But what I've done is I've estimated it linearly. So there's no quadratic term, but I've used a linear estimator when I should be having a nonlinear relationship. Again, that's going to bias your coefficients. And the solution to this is to apply the methods of Chapter 8. So take a look at your data. Think about your data. If it looks like there's a nonlinearity in there, use a log-log model or a log linear or linear log, or add quadratic terms depending on the shape of the nonlinearity, and then that'll be much, much, much better. Okay, this is something new here. Measurement error. And errors, what's called errors in variable bias. So when you have measurement error, and I'm going to show this to you explicitly, you're going to have a problem. And the size of that problem is going to depend upon the degree of the measurement error. And I'll show that very explicitly very, very soon. You might have the wrong responses to surveys. And maybe a survey, use a books example, ask about last year's taxes. And you just kind of guess, oh, I think I paid this amount. Okay, well, that's, you know, maybe on average, people get it right. Some people are too high, some are too low, and across the population it's right. But for every individual, that's going to give you a mismeasured tax burden. So survey, especially when you don't validate the surveys, you just ask people, even simple things like, what's your party affiliation? You'll get biases often not biases, but measurement error in terms of what the truth is. There could be recording errors. Maybe there's rounding. Sometimes data are truncated. You only collect incomes up to a certain level, like $1 million, and every above that just says $1 million and above, so you don't really have good data. There's lots of ways in which this can happen. You know, you take a ruler out and you either mismeasure or you write it down wrong. That would be errors in variable. Now, what happens when you have errors in variable? The problem, as I'm going to show you right now, is the correlation between x and the error is not 0. So let's see if we can see that. So let's take a true model. So the true relationship is yi equals beta naught plus beta 1 xi plus ui. We don't have data on xi without error. Instead, what we have is x tilde I equals xi plus, and I'm going to use wi as the measurement error. Now, it's probably the case that measurement error might average out over a population, like we were saying with the income taxes. Some people guess too high, some guess too low. So if we average over all wi, that has a mean 0, but for any individual, it can be mismeasured. Now, we're going to assume that the correlation between wi and xi is 0. It could be your measurement error is related to the size of x. So it might be when something gets bigger, you're more likely to mismeasure it or something like that. We're not allowing that to happen. So the measurement error, this might just be a normal with mean 0 and variance sigma squared. So there's no correlation. And let's not let there be any correlation between wi and ui. These would just introduce more problems. So it's independent of the error in the actual model. So this is just a random measurement error. That's what this says. It's just a random measurement error. All right. Now let me take this model and rewrite it. I'm going to add and subtract beta 1 x tilde. So let's write it as yi equals beta naught plus beta 1 xi plus beta 1 x tilde I minus beta 1 x tilde I plus ui. So I can write that as yi equals beta 0 plus beta 1 x tilde I plus, and let me put this in brackets, beta 1 times xi minus x tilde I plus ui. So that's now in my error term. See, the regression I'm actually going to run is not y on x, because I don't have data on x, but I do have data on x tilde. That's the variable measure with error. So if I were to run a regression, I'm going to regress yi on x tilde. If I do that, and the truth is the model we started with, this will be our error. Now we know that x tilde I is xi plus wi. So xi minus x tilde I is minus wi. So I can also write this as yi is beta 0 plus beta 1 x tilde I plus beta, ui minus beta 1 wi. Same model, same thing. Here's the problem. Xi, you can see it here. X tilde and x tilde are going to be correlated, right? And so we have a correlation. This is the error term. If I run yi on x tilde, call this vi. Vi is the error term. that we would get in the model. And that error VI would be correlated with X tilde, because X tilde is in it. Or just look at XI here. X tilde I has WI in it. When WI wiggles, XI wiggles. And so WI is correlated with XI. So WI and XI are correlated, and that's going to give us bias. So there's a correlation between X tilde I and VI up here, where VI is that whole error. This is VI too. It's just a different way to write it. And so that's going to lead to bias. In fact, we can actually calculate how much bias we would expect. So let's do that. So I'm going to use this model, this version. So yi is beta 0 plus beta 1 x tilde I plus ui minus beta 1 wi. That's vi. So we can write it as yi is beta 0 plus beta 1 x tilde I plus vi. So that's the model I would actually run. Now earlier we learned that you can always write beta hat, beta 1 hat, as beta 1 plus the covariance of that and that, of x tilde and v, over the variance of that, the variance of x tilde. So if we were to, this is what happens in large samples. So as n goes to infinity, beta 1 hat converges to this. Okay? So but what is the covariance of x tilde is x plus u, and v is u minus beta 1 w. Over the variance of x plus u. That's what's bugging me. Sorry, this is w. X plus w. Make sure to fix that. X tilde is x plus w. I was getting x. So u is uncorrelated with x. It's one of our assumptions. U is uncorrelated with w. W is uncorrelated with x. We already saw that a minute ago. So the only place we get a correlation here is the beta 1. So the top thing is minus beta 1 sigma squared w. The other three terms, when we multiply this out, when you do this, you get the correlation of x with u, the correlation of x with w, the correlation of w with u, and w with w. And the only one that matters that's non-zero is the correlation of w with w. Same thing here. This will be sigma squared x plus sigma squared. And this is w again. I made the same mistake. W. X tilde is x plus w. So now we know that I can plug in for this. So now we know that beta 1 hat converges to beta 1 minus beta 1 times sigma squared w over sigma squared x minus sigma squared w. And so if I just combine the beta 1s, beta 1 hat converges to 1 minus sigma squared w over sigma squared x plus sigma squared w times beta 1. So beta 1 hat goes to sigma squared x over sigma squared x plus sigma squared w times beta 1. So that's the bias, right? This is a number that's less than 1 because we have sigma squared x over sigma squared x plus something, and they're all positive because they're variances. Variances can't be negative. So what do we know here? We can see first that it's biased. So this is less than 1, as I just said. So we can see that it's biased downward. It's too small. The estimated beta is too small. This is a fraction. If this is a half, it'd be half of beta 1. If sigma squared x and sigma squared w are both 1, so this is a half, the estimated would only be half of the true effect. And that's bad. The bias is larger as sigma squared w goes up, holding sigma squared x constant. If sigma squared w is 0, there's no bias. Why is that? Because there's no measurement error. That's when x tilde equals x. It's a mean 0, and there's no variance, so it has to be plus 0. So in that case, there'd be no measurement error. So in general, you get bias. So errors in variables are a problem because it leads to a bias. As long as your measurement error is really small, if sigma squared w is really a small number relative to sigma squared x, then the bias is going to be small. So if you're just measuring, the height of this, there's a chair in front of me here you can't see. If you're just measuring the height of this chair, of course you're going to be off by a little bit. You can't measure it out to an infinite number of decimal places. So if I say, it's 3 feet 6 inches, well, maybe it's 3 feet 6 inches and a little bit more, or a little bit less. I've just rounded, so I've got a little measurement error. But if that measurement error is just really tiny compared to that height of the chair, if this is tiny relative to this number is almost 1, and your bias is not very big. It's only when sigma squared w is large relative to sigma squared x that you have a problem, that you have a lot of bias. In fact, you could write this as beta 1 hat is 1 over 1 plus sigma squared w over sigma squared x, just from algebra. So what matters is that ratio. If this ratio is 0, no bias at all, because you get 1. If sigma squared w is 0, or sigma squared x were infinite. But anywhere else, you're going to get more. You're going to get bias, and the bias is larger when this term gets larger. So it's that ratio of sigma squared w to sigma squared x that really matters. How to fix this? Measure better. So how to fix? Measure better. Go back and redo it. That'd be one way. Instrumental variables, what we talked about in the last example, something that's correlated with x but uncorrelated with the error term. IV estimation is a way to get around the errors in variable problem. And sometimes you can model the measurement error. But that's an uncommon way to get out of this problem. And again, you'll look at this in more detail later. That was measurement error in x. What if there's measurement error in y? So the true model is yi is beta 0 plus beta 1 xi plus ui. But we observe y tilde I is yi plus wi. Measurement error again. And we run the regression, y tilde I is beta 0 plus beta 1 xi plus vi. What's that error going to be? Is it going to be correlated with the x? The answer in this case is no. Let me show you. I can plug in for here. This is yi plus wi is beta 0 plus beta 1 xi plus well, let me make this ui because that's what it would be in this case. Ui. then what's going to happen here is the model would be yi is beta 0 plus beta 1 xi plus ui minus wi. All it does is make your error bigger. Let me do it a different way. That's not the way I want to do this. So you're going to run y tilde I is beta 0 plus beta 1 xi plus ui. That's the model you're actually going to run. But the true model, and this is vi, and the question is, what is vi? So the true model is yi equals beta 0 plus beta 1 xi plus ui. Sorry about this. That's the true model. Now sub in for yi. Yi is y tilde I minus wi equals beta 0 plus beta 1 xi plus ui. So the model we actually run is this one, and the error is ui plus wi. This is vi. So when we run this model, the error is ui plus w. But wi is uncorrelated with x. We made that assumption. Ui is uncorrelated with x. So all that happens if there's measurement error in the yi is that we get bigger standard errors. That's all that happens. So again, the way to show that is start with a true model. Sub in for yi's so you can get y tilde, and then move the error to the other side. And then you've got this. And so measurement error of the y's makes your error bigger, but that's the only consequence. It doesn't cause bias or inconsistency. All right. Missing data. Again, these are all threats to internal validity, and in particular how you can get bias or inconsistency. Missing data in sample selection. And let me just write, so let's do missing data. That's very common, that you'll have data missing that you just don't have observations for, and there's nothing you can do about it. And there's 3 types. First is the missing data are random. Excuse me. Oh, sorry. I had a sneezing attack there. I hope it didn't get too loud on the microphone. I'm very sorry about that. I would have stopped it if I could have. The missing data are random. If the missing data are random, the effect is that the sample size goes down. But that's it. It doesn't have any other negative consequences other than, in effect, you have fewer observations than you would have had if you had all the data. So if you just go through and randomly omit data, that's not going to be a big problem at all. Unless your n gets so small that you can't use the large sample properties or something like that. This is a bigger problem. The missing data is based upon the value of one of the regressors, based on the value of one of the x's. So suppose, as an example, we only take so suppose we use only districts in our class size study where STR is greater than or equal to 20. Well, we could run that regression, but now it's not going to be valid, so regression is no longer valid for STR less than 20 because we don't have that kind of data. So whenever somehow your missing data is related to the x, basically what happens is you then get a correlation between the error term and the x again, and that causes bias. The third way in which missing data could be a problem, the first one wasn't a problem. So if it's random missing data, no problem. If it's non-random missing data, like it's related to an x, that's a problem. And the third is if your missing data are related to the value of y. Last time it was the value of x. This time it's the value of y. Again, that's going to cause a correlation between x and u and lead to bias and inconsistency. The book's example, suppose that we want to predict voting behavior, who's going to win the election. And so what we do is we randomly call people on the phone. But suppose we only call home phones. We don't call cell phones. And there's a difference between the political affiliation of people with cell phones and people with home phones. For instance, suppose that Democrats are more likely to have cell phones only, and Republicans are more likely to have home phones. Then if we only call home, we're going to get a bias because we're going to oversample the number of Republicans, and we're going to think that the election is going to come out one way when in fact it comes out another. And there's lots and lots of examples in the book and elsewhere where this has actually happened in the real world, and you get really bad predictions about who's going to win the presidential election or other sorts of things. And it all comes down to the fact that somehow they were selecting data in a way that was related to what they were trying to measure. It was related to the y. And so in this case, y would be voting behavior, and we're missing all the cell phone people, and that's related to voting behavior. And that's going to cause a bias. So you have to be careful to do that. There are ways to control for sample bias. You can correct your thing ex post if you know you've got too many of one group relative to another. But those are very advanced, and we won't go through them. So if you have missing data, hope that it's randomly missing. Then you're OK. Otherwise, you need to think hard about the kinds of biases those missing data are likely to bring about. OK, I think this was the last one. Yes, number 5, simultaneous causality can cause bias and inconsistency for the same old reason. Correlation of x and u won't be 0. So far, we've assumed that x causes y. So we write y is beta 0 plus beta 1 xi plus ui. This is the treatment, and the treatment causes this outcome. So this is a causal relationship, and we're trying to estimate the causal effect, beta 1 here. Now, suppose that there's two-way causality. Not only does y cause x, but suppose that y also causes x. There's another equation where xi is gamma 0 plus gamma 1 yi plus vi. So now we've got two-way causality. For instance, changing the money supply might cause a change in output, right? We think it does. So money causes changes in output. Money causes output. But it's also the case that when output goes up, people demand more money, and the Fed supplies more money. It's upward sloping supply. So if the Fed accommodates that, and they will if you have a fixed interest rate policy like the Fed has, so if output goes up, that drives money up. So output causes money, and money causes output, so you have two-way causality. That creates a problem if you're trying to figure out if how much m causes y, because it'll create bias. And I'll show you that bias next. Here's how it works. Let me just write the two equations so we can point and do this result easier. So let me just write down the simultaneous causality. So we have the usual causality and reverse causality. Now, look at this. xi has yi in it. When yi wiggles, xi wiggles. But yi has ui in it, right? So this xi has y in it, and y has u in it. So this x and this u are going to be correlated. Let me just plug this in. The first equation is yi is beta 0 plus beta 1 times gamma 0 plus gamma 1 yi plus vi, that's xi, plus ui. And this has ui in it. See, yi has ui in it. When ui wiggles, y wiggles. So because this has u in it, it's going to be correlated with the error. So it's correlated with ui, and that leads to the bias. And so there's ways to fix this. You can use two-stage least squares, which is a special case of instrumental variables that you'll learn in 421. But the point here is that think about it, and if it seems like you have two-way causality, like in the money-income example, then you want to be very careful about how you estimate this and apply more advanced techniques in OLS, techniques that you'll learn in 421. Okay, that's internal validity. Now, let me take a quick drink here. Now let's turn to, we're still doing internal validity, but now we want to look at sources of inconsistency in the standard errors. Of inconsistency / bias in the standard errors. And there's really two main sources here. The first way is heteroscedasticity. We've talked about this a lot already. If we use an estimator that assumes homoscedasticity when the errors are heteroscedastic, that'll give you bias and inconsistency. If we use the heteroscedastic estimator, and in fact it's homoscedastic, that's not a problem. And so that's why throughout the text we've been using the heteroscedastic robust standard errors, because those are going to be correct whether we have it or not. But the other ones are, heteroscedasticity is a really common problem in economics, and so it's best just to assume you have it unless you're really, really sure you don't. And so this is one way in which you could run into trouble if you push the wrong buttons on the computer program. The second one is something called serial correlation. It's also called autocorrelation. And the problem here is the errors are not independent. This is a little bit different problem. This is the identically, remember with the errors are IID, independently and identically distributed. In this case, they're not identically distributed. They have different variances. We can fix that. In this case, they're not independent. So for example, GDP data has autocorrelated standard errors. Say that we're looking at GDP over time, and there's some trend, and maybe that trend has some wiggle to it. And then our actual GDP data has these business cycles. They're a little more irregular than that, but I wanted to show it. So if you have a positive error, it's likely to be followed by a positive error. If you have a negative error, it's likely to be followed by a negative error. And so if you look at the deviations from, if you're estimating this line with these data, this is the actual y. So I say yi is beta 0 plus beta 1 times trend plus ui. There's other problems with this model that you'll learn about later, but these errors are not going to be independent. If ui is greater, if u1 is positive, it's likely that u2 will be positive. It's not always the case. Sometimes you get switches, but positive errors are likely to be followed by positive errors, and negative errors are likely to be followed by negative errors. This causes a large bias in the standard errors if you use OLS. There are other estimators, there's corrections that you can do that get rid of the bias, but you can get really biased standard errors. What will often happen, this is called positive correlation. If positives are likely to be caused by positives, then the standard errors that you estimate will be way too small, and your t's will be way too large, and you'll reject things way too much. So when you have positive correlation, it's called, when positive things are likely to be followed by positive things, you have a big problem. You can often see this. There's a test for this. It's called the Durbin-Watson test that you can use, and you'll learn how to do that in 421. So there's a diagnostic for this. There's also other tests like a Q test and others that you can use to test for serial correlation. And so what you do in this case is you first test for the serial correlation. If the test is significant, if it looks like you have it, then you use a correction that gets rid of this problem. For now, what you need to know is that if you have serial correlation, then you're going to have a problem. It's not your betas are fine in this case. On average, you get the right betas, but you get really, really bad estimates of the standard errors. Often they're way too small, and that makes your t-statistics way, way too big. So far, when we first started, we said there's two ways that you can use regression models. One is to learn about the world. So we want to learn about causal effects, learn about these betas, what are the parameters, and what's their actual magnitude in the world. So we're learning about how the world works by estimating these betas, and we want the truth, so we want them unbiased, and so on. We can also use them for forecasting. We made the point very early on that for forecasting, we don't even need to have causality. And that's the umbrellas and raining example. You know, you can use the number of umbrellas to forecast the weather, but umbrellas don't cause the weather. And so there's differences between forecasting and other uses. For instance, you might run score hat equals 698.9 minus 2.28. That's the model we started with times class size. So that's the estimated model. So you run this regression. And you're a parent, and all you care about is the quality of schools. So you're trying to predict or forecast the quality of schools. And so you run this regression. This regression might predict fairly well. And the reason is this STR variable not only will pick up the effect of class size, but it can pick up all those other effects we've talked about, like income. Part of this might be because higher income districts have lower class sizes, and it's really income that's causing score. It may be that immigration is correlated with STR, but it's really immigration that's causing score. If I leave all those other variables out of the model, this coefficient will be very biased in terms of its effect of STR. But that's not what the parent cares about. All the parent cares about is, I want to forecast the quality of the schools. And for forecasting, you don't often care as much about the bias, and you're not trying to learn about the world. What you want to get is a good forecast. So this number might be a really lousy estimate of the effect of class size because it picks up all those other effects. But because all those other effects are in there, it might be an okay predictor of how well those schools do on test scores. So this still might give you a way to predict which schools are better and worse just by looking at their class sizes, even though the model itself is not very good. For forecasting, the biggest concern is not internal validity so much, it's external validity, because you're often forecasting outside the range of your data. In macro, you necessarily are. And so I've got data from 1959 to today, say, and I want to predict what's going to happen a year from now. Well, that's outside the range of my sample. That's an external validity question. Will it work? Will the economic environment and social environment be the same? Will the population be the same? For instance, there's large demographic change going on right now. Maybe something I estimate now might not hold in the future because the population's different in terms of the average age and the average characteristic of people. And so for all those reasons, you'd worry about external validity. And so for forecasting, in fact, it's the external validity that's usually what you care about. Also, for forecasting, you may not even care about bias. Suppose I have two estimators of beta hat. One of them is unbiased, and it looks, here's the distribution of it. So it's centered on the truth. But man, it has a big variance. So the truth might be 10, but you could get minus 20 or 20 or way far from the actual true value because there's such a large variance in your estimate. Now you have another estimator that's available to you that is slightly biased, but has a really tight distribution. So it's not centered on the truth, but you might get closer on average. If you're trying not to lose a lot of money and it's important that you forecast beta, get as close as you can, you might get a lot closer using this bias estimator on average than you would using the other estimator. So with forecasting, you're often willing to accept a little bit of bias, and maybe it's even tighter, closer to this, for a big reduction in the variance of the estimator. And so what you often do with forecasting models, unlike what we're trying to learn about causal effects, is just throw in the kitchen sink. Just throw in all the variables you can think of that might possibly cause anything. In general, when you do that, you're going to get all sorts of multicollinearity and all sorts. You might throw in irrelevant variables. When you use variables, when you throw in variables that don't matter for y, but you've included them, it makes your standard errors go up, but you're not doing t-tests, you're forecasting. And so often you just throw in everything you can think of for forecasting, and you accept little biases for big reductions in the standard errors. And the book goes through this class size example at the end of the chapter. It's mostly things we've looked at before and done before, but they kind of apply these concepts we've talked about. I encourage you to read that. It's a good check on your understanding. But guess what? We finished chapter 9, and that is the last chapter. So thank you very much.